Hello all, and welcome to the conics sections, video number 7. Yes, that's right. We are on video number 7 in this conics section series. In this video, we move on to our fourth and final conic, the hyperbola. The purpose of this video is to show you the standard form equations of a hyperbola and teach you how to graph a hyperbola from its equation, and finally, how to identify the special pieces for a hyperbola. Of course, hyperbolas can go sideways, as you see here in the left, or hyperbolas can go up and down, as you see me highlighting here on the right. Remember when we first introduced the conics, a hyperbola kind of looks like two parabolas. It isn't, but that's what it looks like. And please understand, in these complicated looking diagrams, the hyperbola is just the green part. The hyperbola is just the green part. All those other things that you see here in the diagrams are things we use to draw the hyperbola. If you look in the bottom left, this is the standard form equation of a hyperbola that goes left and right, or opens sideways, or is a horizontal hyperbola. On the right, there's the standard form equation of an up and down hyperbola, a vertical hyperbola. Notice the equations look very similar to the ellipse equations, but they aren't quite. A hyperbola equation subtracts the squared terms. And you might recall that with ellipses, we're adding the squared terms. You might also recall with ellipses, a squared was always the bigger denominator. Not so with hyperbolas. With hyperbolas, a squared is always the first denominator. Might be bigger, might be smaller, doesn't matter. It's the first denominator. A squared is always the first denominator. If a squared is under x squared, or x squared comes first, your hyperbola goes in the x direction. It's sideways, it's horizontal. If a squared is under y squared, or y squared comes first, your hyperbola goes in the y direction, or it's up and down, or vertical. Let's look at the diagrams here. You might recall that a parabola had one vertex. An ellipse had 4 vertices, 2 vertices, 2 co-vertices. Well, a hyperbola has 2 vertices. Vertex, 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 vertex. Letter A is the distance from the center to a vertex. So that would be the same as in ellipses. Center to vertex is A units. Center to vertex, A units. Center to vertex, A units. Center to vertex, A units. And of course, the center of all these hyperbolas today will be at 0, 0. Letter B. B is the distance from the center to this point you see here on the dotted rectangle. B is the distance from the center to that point on the dotted rectangle. In the right-hand diagram, this is letter B. That's letter B. And that's needed when we actually draw a hyperbola from its equation. You'll see that in our first example when we get there. With ellipses, remember we had the major and minor axis. We do with hyperbolas as well, but we don't call them that. In the hyperbola world, we call the major axis the transverse axis. So vertex to vertex is the major or transverse axis. On an up and down one, vertex to vertex, the major or transverse axis. It's not labeled on this diagram, but if you go from this point to this point, that's the minor axis, or in the hyperbola world, we call that the conjugate axis. In the one on the right, this point to this point, the minor or conjugate axis. You may recall that ellipses had two focus points, or two foci. So it is with hyperbolas. They're always on the major axis, so to speak. They're inside each curve of the hyperbola. There's a focus, and on the up and down one, here's a focus, here's a focus. Just like with the ellipses, letter C is the distance from the center to a focus. So from center to a focus is letter C. Center to a focus, letter C. Center to a focus, C units, and center to a focus, C units. Here's the equation that relates A, B, and C. For ellipses, it was C squared equals A squared minus B squared. For hyperbolas, it's C squared equals A squared plus B squared. It's really easy to remember for hyperbolas, because you might notice it's really the same as the Pythagorean theorem. One last thing. You'll notice these dotted lines. This will probably be something new for us. These are called asymptotes. It's one of those fun math words to say, asymptotes. Here they are on the vertical one, the up and down one. Asymptotes. Let's come up with a definition for an asymptote. Right now, let's just say that it's a sacred boundary line. Your hyperbola will never touch or cross an asymptote, but they serve as kind of a sacred boundary line. When we get into identifying the special pieces of a hyperbola, sometimes we will want to know the equations of the asymptotes. For a sideways hyperbola, they are y equals pos neg b over ax. And for an up and down hyperbola, the equations of the asymptotes are y equals pos neg a over b x. So kind of like with ellipses, these diagrams get a little bit overwhelming. There's just a lot of information, a lot of pieces to understand what they are and what those letters represent. But that's what they are for hyperbolas. Let's actually get to an example. Let's graph 25y squared minus 4x squared equals 100. Well, the first thing we need to do is put it in standard form. which is having a 1 on the right side of the equation. So let's divide both sides of our equation by 100. That would give us y squared over 4 minus x squared over 25 equals 1. And we can think of 4 as 2 squared. We can think of 25 as 5 squared. We know the center, 0, 0. We know, since y squared comes first, that this is an up and down or vertical hyperbola. Remember that the first denominator is a squared, so a is 2. That makes b 5. So here is the technique for graphing your hyperbola. From the center, let's go a units up and down. 1, 2, vertex, 1, 2, vertex. From the center, let's go b units in the x direction. 1, 2, 3, 4, 5. Let's just say a point. And 1, 2, 3, 4, 5. Let's just say a point. Next, you would draw a dotted rectangle through the two vertices and those 2 points. Then you sketch in the asymptotes. The asymptotes go through the center and the corners of the dotted rectangle. Speeding up a little bit here. And folks, that is the framework for your hyperbola. Now we can draw it in. I'm going to switch colors. Your hyperbola will go through the vertices, and it will come up here, and I like to say it will hug the asymptote. They're a very affectionate shape. It comes out here and it will hug the asymptote. That means as it takes off toward infinity, it will get closer and closer and closer to your asymptote, but never touch or cross it. And here's the other half. Through the vertex, hug the asymptote, hug the asymptote. So the hyperbola itself is just the blue. The green is the framework that we need to graph it. Very unique approach to graphing, because with any other shape that we graph, we always plot some points on the graph to produce it. With hyperbolas, the only points we plot on the hyperbola are the 2 vertices. We sketch it in with the framework created by the asymptotes. Let's find the special pieces. Let's go after the foci. To find the foci, we need the value of c. Remember, this is the equation that relates a, b, and c. So c squared equals a squared plus b squared. C squared is 29. That means c is the square root of 29. Exactly, or approximately 5 point something for counting purposes. So, from the center of the hyperbola, in the direction of the major axis, the transverse axis, let's count radical 29 units. Here we go. 1, 2, 3, 4, 5 point something. Focus. And that would be the point 0 radical 29. And in the other direction, 1, 2, 3, 4, 5 point something. Focus. That would be the ordered pair 0, negative radical 29. Last thing, let's find the equations of the asymptotes. Remember, for an up and down hyperbola, we said they were y equals pos neg a over b x. So in this case, it would be pos neg 2 over 5x. Obviously, this one would be the negative 2/5 x because it goes downhill from left to right, has a negative slope. Obviously, this one would be the positive 2/5 x, having a positive slope or going uphill from left to right. And there you have it, folks. That's how we graph a hyperbola and find all of its special pieces. Hope you found that to be informative. Thanks for watching.